Let's do average atomic mass really quickly. Okay, all you're going to do, guys, convert your percents into decimals by moving it 2 places to the left, 2 decimal places to the left, multiply your percent abundance by your mass number, and add them all up. So for this one, 92.21%, you're going to move your decimal place 2 places. So this becomes 0.9221 times 28. You're going to add that to, well, 1, 2, so that's 0.0470 times 29 plus 2 places, 0.0309 times 30. Okay, so do all of that math, and what I think you end up getting is 28.11 rounded, and please round to just about like 2 decimal places. Your units are AMU. And we're done. All right, guys, so we're starting with number 22. We're trying to, first of all, figure out number of significant figures. Remember, if your decimal place, here's my United States, if it's present, you count from, sorry, really bad United States, left to right. If it's absent, you count from right to left. Okay, so in this case, it's absent, so I'm going to be counting from right to left. I can start on a 3 because that's not a 0. So it's 1, 2, 3, 4 significant figures. Okay, now I need to put this into scientific notation. And so what I'm going to do is the following. I need this number to be between 1 and 10. So I'm going to take this imaginary decimal place and move it 1, 2, 3 places. Okay, now, so this is going to be 2.323 times 10 to the something third. Okay, negative or positive. Well, I took a really big number and I made it small. So it needs to be a positive exponent because if you can imagine, this is 2 about times 1,000, which gives you 2,000. So that's a nice way to be able to check yourself. Okay? All right, here, remember, my decimal place is present, so I'm going to be counting from left to right. I can start on this 1, so it's 1, 2, 3 significant figures. And I need to make this number between 1 and 10. So I need to take this decimal place, move it to the right 1 place, which gives me 1.23 times 10 to the, well, I only moved it 1 place, but I made a small number bigger, which means it has to be a negative exponent. Okay, when you make a small number bigger, make it negative exponent, and it's negative 1 because I only moved it 1 place. Okay, look at this one. I have, since my decimal place is present, I have 1, 2, 3 significant figures, not too bad. And I'm multiplying it by a number that has a positive exponent. So I'm going to be making this number bigger since this exponent is positive, meaning moving my decimal to the right. So I'm going to be moving it 1, 2, 3, 4, 5 decimal places, which means those spaces are going to be filled by 3 zeros. So 3, 0, 3, 1, 2, 3, and I'm done. Okay? For this problem, first thing you have to decide is how many protons does aluminum have? And well, it has 13 if you look at your periodic table, which means this neutral atom of aluminum has to have 13 electrons to be neutral. Okay, so what we're going to do, I'm going to draw 13 protons in the center. Okay, if you look at your periodic table, in the first energy level surrounding your nucleus, you can only fit 2 electrons. Remember, you have a 1s2, meaning only 2 electrons, and that's the only thing that can fit into your first energy level. Okay, and so only 2 electrons in your first energy level, so I'm going to put 2 electrons. If you look at your periodic table, in your second energy level, you can fit 8 because you have 2s2 and 2p6, so a total of 8 valence electrons. So in my second energy level, I'm going to put 8 valence electrons. Now, if you notice, up till now we've used 10 total valence electrons, and I want to use 13. So in my third energy level, okay, I'm going to fill it with the rest of my valence electrons, which is only 3 that are left over. Okay, so in this problem, guys, I'm not going to have you use a bunch of them because as you go further and further out, you can fit more and more electrons. So I'm only going to have you use like up till the third energy level, principal energy level, but just for you to know, first energy level, only 2, second can only fit 8, and then the third, that'll have the rest of your electrons, which is 3. Okay? When you have Al3+, guys, what happens is you lose these 3 electrons. Okay, that's the whole point. That's what gives you your +3 charge. So you still got your 13P+, you still got your 13 protons. That hasn't changed. But now all of a sudden you still got 2 electrons, you still got 8 electrons in this one. But now you don't have this third energy level at all because you got rid of 3 electrons. That is why cations, which this is right there, that Al3+ is a cation, it's positively charged. Cations are bigger than their regular element because they've lost 3 electrons. They've lost that whole outer energy level. Okay? Alrighty, let's go on to number 24. Okay, so this is some naming. So the first thing you need to do is decide whether you have an ionic or a covalent compound. As soon as you see dinitrogen, you should be thinking, oh crap, I've got some prefixes that's going to be covalent automatically. Covalent is the only one that uses prefixes. Okay? When you have covalent, that means when you write the formula, you don't have to cross your charges because I already tell you how much of each there is. For nitrogen, N, di means 2, so there are 2 nitrogens. And for oxygen, pent means 5, so there are 5 oxygens. And you're done. No crossing of charges. Quite nice. Okay? When you're creating ionic compounds, yes, you do have to cross your charges. Okay? All right, so for Na2SO4, Na is a metal. Automatically, I know as soon as I see a metal and a nonmetal, it's ionic. Okay? So for ionic, you don't use prefixes. So this is just going to be sodium sulfate. And sulfate because that is a polyatomic ion. Okay? No di, no Roman numerals yet, and I'll explain those in a second. You're done. They're really easy to name. Okay? PCl3 is actually, since P is a nonmetal and Cl is a nonmetal, this is going to be covalent. Okay? So for phosphorus, I've only got 1 phosphorus, but I'm not going to put mono because for the first element, guys, you don't put mono. You do for the second if you only have 1 of them. So I'm just going to put phosphorus here. Okay? And then how many chlorides? Well, I've got 3, so it's trichloride because I need to use prefixes when it's covalent and only when it's covalent. Okay, let's look at the last one. FeBr3. Well, Fe is a metal, and so therefore my compound is going to be ionic. That's nice and easy. But if you notice, Fe on your periodic table is a transition metal. Therefore, I need to use my Roman numerals to demonstrate the charge of Fe. Well, if I uncross my charges, here's the 3, and make that the charge of Fe, I've already determined the charge. Really nice and simple. So when I write out my name, it's going to be iron, in parentheses, a Roman numeral 3, so it's bromine, but remember, it has to have an IDE ending at the end, bromide. The only time you don't have to have the IDE ending is when you have a polyatomic ion. Okay? All right, for 25, as you move across the periodic table, the atomic radius, it is going to decrease. And the reason why it decreases, guys, is because you're increasing your number of protons. Now, protons will then attract your electrons, decreasing the size of your atom. Okay? As you move down your periodic table, the atomic radius will increase. And the reason why it increases is because you go from just having a 1s, right, to going to 2s, to 3s, to all of those principal energy. You're increasing your principal energy levels, right? You have much more of those actual level of those circles around it from the Bohr's model, even though that's not technically correct, but you can imagine it like that. So just one as before, like at the very top, and then you start getting more and more and more circles. So you increase your number of principal energy levels. And sorry, I'm using shorthand. It's hard to write with this. Energy levels. Okay. Remember, for your electronegativity and for ionization energy, it is the exact inverse of atomic radius. Therefore, as you move across the period, since your atomic radius decreases, this is going to increase. As you move down the period, since this increases, right, this is going to decrease. Okay, and that's why it increases, because this is decreasing. Cool. All right, remember, for double replacement, you need to do innies and outies. So you have Na NCl, and Ba and CO3. Remember, the charge of Na is +1, charge of Cl is -1. Therefore, when I create my compound, it's just going to be NaCl, and I'm done. Okay, ignore those 2's for right now. Now, the charge of Ba is +2, the charge of CO3 is -2. Therefore, when I create my compound, those 2's cancel each other out, right? Because otherwise I would just have Ba2, CO3, 2. These cancel each other out, and I just end up with BaCO3. Now, I need to balance, okay? So I have 2 NAs here, so I need to put a 2 here. I've got 2 CLs, 1 BA, 1 BA, 1 CO3, it's a polyatomic ion, carbonate, 1 CO3, good. Now, determine what's soluble, insoluble, so I can write my full ionic. Okay, your reactants will always be soluble. You don't even need to check on them, I promise you they will be. Okay, you need to check on these. What you'll find is this is going to be soluble and this is going to be insoluble. This is a carbonate. You need to know the names or else you can't find your rules. Okay? So I'm going to break up Na and CO3 first. So how many NAs do I have? Well, I have 2. So it's 2 Na plus, well, I have 1 CO3 and its charge is 2 minus, plus I've got 1 Ba there, so Ba2 plus. Okay, I've got 2 Cl, so plus 2 Cl minus, gives me, I'm going to break up my NaCl since it's soluble, 2 Na plus 2 Cl minus, and I'm going to leave my BaCO3 alone since it's insoluble. Now I'm going to cross off anything that's the same on either side, so I'm going to cross this off, that off, that off, and that off. Okay, and I end up with Ba 2 plus CO3 2 minus, 2, minus, plus, gives me BaCO3, and I'm done. Okay, my spectator ions are the ones that aren't involved in the reaction, which are Na plus and Cl minus. Those are the ones I crossed out.